All right, we're going to finish up our discussion on Taylor series by looking at this last little bit that's just about working with Taylor series. So what are these good for? How can we use them? All that kind of stuff. There's not going to be a really exhaustive discussion of that here, but this will hopefully give us at least a little bit of an idea about what's really going on with these Taylor series and why they might be helpful, or some of the reasons why they might be helpful. So first, we're just going to do a quick little recap, a little discussion on how we might find a Taylor series for a function, and then we'll take a look at three main topics from calculus: limits, derivatives, and integrals, and we'll try and see how Taylor series might help in each of these cases. And then at the very end of this, we'll do a couple of examples of connecting some power series or Taylor series with functions. So we'll start with just a nice little recap. This is normally a discussion prompt that I might give at the beginning of one of my face-to-face classes, where I'll put this function up on the board and I'll say, find a Taylor series centered at x equals 0 and the interval of convergence for this function 2x times the cosine of x squared. And what I'll normally do is give them kind of a discussion prompt that says, really, I don't actually really need you to find it. I want you to figure out how you would find it. Describe what you might do to find the Taylor series centered at x equals 0. So go ahead, pause this video for a second, and try and recreate that little activity. Just see if you can describe how you might find this Taylor series for this function. All right, if you're back, I'll give you a bit of a hint and maybe make you think about this again. One of the ways of doing this is to certainly just write out all of the derivatives, or at least the first several derivatives of 2x cosine x squared. Evaluate those derivatives at 0, divide them by the correct or respective factorials, and see if you can come up with some general form for the coefficient structure, right? We know the coefficient structure of a Taylor series looks like f raised to the kth derivative, we'll say, at, in this case, 0 over k factorial, and then we'll just keep multiplying these by x to the k, because x minus our center 0. So we know that this is going to be the structure of it, right? Here it is. This is the Taylor series. But what we care about is trying to find a general form of this, but for this function specifically. So you certainly could do that. That's hard, though. If you've started thinking about that, you'll notice that derivatives of 2x cosine x squared are going to be annoying. You're going to have to do the product rule and the chain rule every time. You're going to get a whole bunch of big terms. Some of those things are going to be okay to evaluate. Some of them will be a little bit annoying, whatever. This could be a frustrating problem to work with. So see if you can think about a different way of doing this. Pause the video again. We'll come back in a little bit and see if we can describe this a little bit differently. All right, I've got three possibilities here. The first is just what we said last time. You can find a bunch of those derivatives, evaluate them at 0, and then here's our structure, right? That's hard. What we could also notice, though, is that this is just a combination of functions that we might already know. We can compose x squared into the cosine Taylor series, which maybe we already know that, right? The cosine Taylor series is the one with all of those even exponents, even factorials. So we've got this series here for our cosine. It's alternating, and we've got x to the 2k over 2k factorial. Hopefully you found that sometime between that last video and this one. And then you could compose x squared inside of this thing using our properties of power series, and then you could multiply by this power function 2x. That works. That'll do it for you. Similarly, you could take the sine Taylor series, the one that has the odd exponents in factorials. That's our negative 1 to the k times x to the 2k plus 1 all over 2k plus 1. And you could notice that if we look at the derivative of sine of x squared, the chain rule says that that's 2x cosine x squared. So you could compose x squared into this sine Taylor series and differentiate it. We found out last time in our properties that we can integrate and differentiate Taylor series or power series, what we were talking about, pretty well. Or maybe this wasn't last time. Maybe this was two videos ago. I'm losing track of time. But we have these properties of power series that we can work with. So a couple of ways of doing this one. We will revisit this and we'll take a look at this third option a little bit later. These, though, will hopefully be a little bit easier than just writing out all the terms by hand and trying to find a pattern for them. Okay, anyways, let's move on to working with Taylor series, but hopefully that's a nice little reminder about Taylor series. The main idea is that polynomial functions are pretty easy to work with in calculus. When you're thinking about limits and derivatives and integrals, polynomial functions are like the easiest ones. For limits, we have this nice property that says polynomial functions are continuous everywhere, which means that limits are really easy because they're the same as the function values. So you can just evaluate your function at an x value to find the limit as x is approaching that x value. Polynomial functions, easy to work with. For derivatives, we have the power rule, and we have this property that says you can differentiate these things term by term, split them up over sums and differences. And the power rule says just bring your exponent out front and subtract one for each of those terms. Polynomial functions, easy to work with. For integrals, same thing. We can split them up by sums and differences, so we can look at them term by term. We have our power rule that says for integration, we're going to add 1 to every exponent and divide by that coefficient or by that exponent, sorry. So again, polynomial functions are easy to work with. So the Taylor representations of functions should be easy to work with as well, because you can think of these as infinite degree polynomials. We're still going to be able to deal with sums and differences nicely. We'll still be able to do power rule really easily. Things should still go pretty well. So let's consider this example for limits. If we wanted to do this limit in kind of the normal way, we'll say, without Taylor series, if I gave this to one of my Calc 1 classes, what they would do is they'd say, all right, let's see. This looks like continuous functions on the top and bottom. Maybe we'll divide by 0, but let's check out what's happening when you evaluate. 0 squared plus 2 cosine 0 minus 2 over 3 times 0 to the 4th. And they'd say, oh no, 0 over 0. What do we do? L'Hopital's rule. So they're going to look at this limit. Oops, I need a sine x there. And then we've got 12x cubed. And you'll notice, again, you get 0 over 0. So they'll say, all right, L'Hopital's rule. So this is 2 minus 2 cosine x over 36x squared. And again, you get 0 over 0. So again, we do L'Hopital's rule. So this is 2 sine x over 72x, and oh my gosh, we still have another 0 over 0. So again, L'Hopital's rule. I'll try gray for my next color. I'm running out of colors to use. I like to change my colors every time I differentiate things. 2 cosine x over 72. All of this to say 2 over 72, which is 1 over 36. Ugh. Let's see. This is 1, 2, 3, 4 rounds of L'Hopital's rule on this. Not an easy problem. Now, okay, it's actually not bad. L'Hopital's rule is not hard to apply here because there's not any like crazy derivatives or there's not any weird manipulation that we have to do. But if I gave this to an intro calc student, they might get a little overwhelmed just by having to do this so many times, right? They might eventually say like, all right, does this limit just like not exist or something? It's hard to maybe know that you're supposed to have the stamina to go through L'Hopital's rule 4 different times. Now, this is just by nature of the way this limit is set up. But let's just take a look at an alternate way of evaluating this limit where we're going to use the fact that cosine of x is this nice Taylor series of all the even exponents, -1 raised to the k, x to the 2k, over that 2k factorial. Now, I'm going to put it in like this so that we can see all of the terms. But let's go ahead and chuck this in right here for our cosine of x. So our limit now is x squared plus 2 times 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus minus blah, blah, blah. And then I've got a minus 2 all over 3x to the 4. Well, what you can notice is that we can just do the distributive property. So this is really, oops, I need my limit statement. X squared plus 2 minus, notice 2x squared over 2 factorial, that's just x squared. And then after that, I'll leave it as like 2x to the 4 over 4 factorial. Actually, you know what? Let me figure this out. 2 over 4 factorial is really 2 over 4 times 3 times 2. So this is 1 over 4 times 3. So it's x to the 4 over 12. This one I'm not going to mess with. There. And then I've got a minus 2 at the end. And that's all over 3x to the 4. Notice x squared minus x squared, 2 minus 2. Those things are just going to go away. So this is really a limit as x goes to 0 of x to the 4 over 12 minus 2x to the 6 over 6 factorial plus minus forever over 3x to the 4. And now what you can notice is that we can cancel some stuff. So this is really going to be the x to the 4 over x to the 4 is going to cancel out. We've got 1 over 12 divided by 3, so that's 1 over 36. Then we have minus 2 over 3 times 6 factorial, and now there's an x squared here, plus minus, etc., etc., etc. And you'll notice that for all the bigger exponents, they're still going to have power terms in them. So now, when we take a look at x going to 0, all of those terms are going to equal 0, but this first constant is going to be left. So hey, we get 1 over 36 again, just like we were supposed to, but in this case, we didn't have to use L'Hopital's rule 4 times. Now, I'll leave it up to you as to whether you think that might be easier or harder to do. It's kind of your own personal choice. But I do at least want to show you that we can at least approach this using Taylor series instead of having to deal with L'Hopital's rule. All right, let's do that example that I started things off with where we can talk about derivatives. There's lots of things that you can do with derivatives of Taylor series. You can confirm for yourself that the derivative of the sine function really is cosine. You can show that the derivative of the exponential function is itself by just differentiating the Taylor series. But what I want to do is find the Taylor series for sine of x squared, and then we'll differentiate that. Because we know that the derivative of sine of x squared is equal to 2, x cosine x squared by the chain rule. So, my sine of x function, I know that that's the sum from k equals 0 up to infinity of negative 1 to the k of x to the 2k plus 1 over 2k plus 1 factorial. And if you don't know that, go ahead, look that back up, and see if you can start committing this one to memory. We should commit to memory the sine of x series, the cosine of x series, and the exponential e to the x series at least. If you don't commit them to memory, it's not a huge deal. We could find this because it's easy enough to build the derivatives, find the coefficient structure, and everything should go quickly. But if we just remember, oh yeah, sine is the one that's got the odd exponents because it's odd symmetric and it's alternating, everything goes pretty well. All right, so then I know that sine of x squared is going to be this Taylor series with x squared plugged in for x. So it's going to be the series from k equals 0 up to infinity of negative 1 to the k of x squared raised to the 2k plus 1 all over 2k plus 1 factorial. And I can simplify that a little bit because I know that that's negative 1 to the k of x to the 4k plus 2 when I multiply those exponents divided by 2k plus 1 factorial. Great. Now I can do the second step where I differentiate this thing. That's going to be the derivative of this Taylor series. Now we can be pretty clever here. Because remember I said derivatives like limits, are easy to work with polynomial functions. Let's think about what this thing is. This is an infinite degree polynomial, essentially, where the first term is positive, negative 1 to the 0, x to the 2 power. And the second term, divided by, 1 factorial. And the second term is negative 1 to the first, x to the 6th power over 3 factorial. And then we have positive x to the etc., etc., etc. We can differentiate each of those terms, though. So what I've done is I've just put the derivative on the term structure itself. Then you can notice that there's a bunch of stuff in here that doesn't even have any x's in it. The only thing that's going to get differentiated is this x to the 4k plus 2. And now our derivative rule should take over. We're going to bring a 4k plus 2 out front, and we're going to subtract 1 from our exponent. So we've got negative 1 to the k times 4k plus 2 over 2k plus 1 factorial times x to the 4k plus 1. And that's a Taylor series structure for x squared sine of, this thing here, 2x cosine x squared. There we go. You should go ahead and check that and see if it's the same as what you got when you took the cosine thing, composed x squared inside of that, and multiplied it by 2x. It might not look exactly the same, and that's okay, because what you'll notice is that for this term here, you can factor out a 2k plus 1 and then cancel some stuff. So what you might have is that it's actually represented when you do it the other way in this form. The 2k plus 1 factors out, and we're just left with a 2. And then our factorial cancels, and we're just left with a 2k factorial. So you might have something that looks like that instead when you do it in a different form. Pretty cool. All right, integration. We've talked about this kind of an integral for a little while. Oops, there's supposed to be a squared here. This first one right here is not hard, right? That suddenly makes it a lot harder. So what we might do is find the Taylor series representation for sine of x squared, and then we can find the antiderivative. I should have said antiderivative here. That is, yeah. The Taylor series representation for the antiderivative of sine of x squared. Cool. The integral of sine of x squared, and evaluate it from 0 to 3. So we'll find the Taylor series representation for sine of x squared. We'll antidifferentiate each term, just like we did before, and then we can evaluate that antiderivative from 0 to 3. So as a reminder, sine of x is this nice Taylor series here. And again, as a reminder, we've already done this. We found the Taylor series for sine of x squared. It's this one in red. So it's going to be raised to the 4k plus 2 over the 2k plus 1 factorial. So we'll say sine of x squared is this series and now instead of differentiating it, if we want to find the integral of sine of x squared dx, that's really the integral of this series I need an x to the 4k plus 2 all over 2k plus 1 dx. And then just like we did with the derivative, we can say this is the sum from k equals 0 up to infinity of, I'm going to pull out the negative 1 to the k over the 2k plus 1 factorial. And I'll say this is an integral of just x to the 4k plus 2 dx. We're just going to antidifferentiate each term, and so this is all really inside of our sum. Our antiderivative of this little power function, though, is really easy. So we have a sum of k equals 0 up to infinity of negative 1 to the k over 2k plus 1 factorial times x to the 4k plus 3 over 4k plus 3. And then, of course, we have like a plus c here. But remember, when we tack on these limits of integration, what we're really going to be doing is evaluating this whole thing from 0 to 3. So let's go ahead and do that. We'll plug in 3 for x. This is negative 1 to the k, and now we have 3 to the 4k plus 3 over 2k plus 1 factorial times 4k plus 3 minus whatever happens when you put in 0, which is just 0. So we're left with just this series. This series, notice it's not a power series, this infinite series is the representation of this area here. Okay, well that's not super helpful because we'd still need to know what this converges to. Well, guess what? This is an alternating series. And so if you look back, there is a theorem that tells us how to approximate alternating series to whatever degree of margin of error, whatever degree of accuracy that you'd like. We have to go out to n number of terms in our partial sum, where the n plus first term, the next term after that, is smaller than whatever margin of error we'd like. That's not actually that difficult to do. We could whip up a computer program really quick, a couple of lines of code in Python, that you would be able to approximate this series to whatever degree accuracy you'd like. What we'll find is that that's much faster at approximating that area than it is to use a Riemann sum. If you go back to Calc 1 and approximate this area using a Riemann sum, you're going to have to use a lot more terms of that Riemann sum, a lot more rectangles, than you would for this Taylor series approximation of it. So that's pretty cool. That works out really nicely. All right, our last topic, we're going to connect some power series to functions themselves. What we've normally been doing, though, is taking a function and writing the power series representation of it. We're going to do this backwards now. We're going to say, what if we have some series and we want to recognize what they are? So we'll do a basic one first, where we just recognize the form of a, I'll put it in quotes, a known series. So it's going to be some kind of like transformed version of a series that we hopefully will recognize. Then we'll look at a harder one where we have to be really, really clever to notice a connection. And I'll try and point out the kinds of connections that we'll look for. Hopefully this example will be helpful. And then I've got another one where we'll evaluate a convergent series, not a power series, just a convergent series by recognizing it as a function output. This is a cool one. All right, so here we go. First example, this is the, quote, easy one where we're going to recognize a known series. What I want you to do is to just sit here and think about this thing. Look at this series and see if you can find some structure that you recognize. What is the coefficient structure on here? What are you doing to all these terms? What kind of factorials do you have? And do you recognize that? Pause this video and think about that for a couple minutes. Maybe you recognize it a little bit better when I've got this written up here. Doesn't this kind of look like an exponential function? Except instead of x to the k, we have this 1 minus 2x to the k. So this is like an exponential Taylor series. But 1 minus 2x is composed inside of it. So doesn't this make sense that this is just really e to the 1 minus 2x? Because if we went backwards, if I gave you this function and said find the Taylor series representation, we wouldn't differentiate this and figure out how it all looked. What you'd do is you'd say, oh, okay, that's an exponential function with 1 minus 2x composed inside. Let's compose it into the Taylor series. So we're just going backwards here. Our interval of convergence, we'd have to say, all right, we need 1 minus 2x to be in negative infinity to infinity. And this leads us to x being in that. So x is all real numbers So I'll just say x is in this interval. So here's our interval of convergence. It's going to converge everywhere, which is really great. Cool. Not that hard if you can recognize it. So try and get used to recognizing the form of that exponential, the stuff raised to the k over k factorial, the sine and cosine ones where you've got odd and even exponents and odd and even factorials, and then you've got this alternation going on. Try and recognize those forms so that when we see things that are similar to it, we can try and make those connections. Second example, a little bit harder. If you look at this, you're going to notice very quickly that this does not have any of those forms that we were hoping to recognize. What I do want to notice, though, is this. So first off, this is a little bit different. We have a straight up k sitting in the numerator. We haven't really seen that before, right? So the question is, where could the k in front come from? Whoops, my tablet shifted, so I wrote it way up there. What kind of thing could we have done that would bring a k out to a coefficient? Doesn't it kind of seem like we could have differentiated? Doesn't k x to the k kind of look like a derivative rule? Kind of looks like power rule. But we would need a k minus 1 here, right? Because we know that the derivative of x to the k would be k x to the k minus 1. So let's go ahead and do that. Let's put a k minus 1 in here. But to offset that, we'll put another x. Now, if we write this as k x to the k minus 1 times x, then we've got a derivative of x to the k here. So let me rewrite this. Say this is negative 1 to the k times x over 4 to the k times the derivative of x to the k. And that's all inside of our series. Now what you'll notice, though, is that this x we can bring out front of our series because it has nothing to do with this. So this is just x times the sum from k equals 0 up to infinity of, notice these coefficients we can put in the derivative. So this is really the derivative of negative 1 to the k, x to the k, over 4 to the k. And now I'm going to swap this derivative out here. And I'm going to say this is x times the derivative of this whole series. Now this is great because I can say this is negative x over 4 to the k. And this series here is geometric. R is equal to negative x over 4. So right off the bat, I know what this thing is going to converge to. This thing is going to converge to 1 over 1 minus negative x over 4 if the absolute value of negative x over 4 is less than 1. Or you can say the absolute value of x is less than 4. So our interval of convergence is negative 4 to 4. And now we can say this thing is really x times the derivative of negative 1 over 1 plus x over 4. If you want, you could rewrite this as x times the derivative of 1 over 4 plus x over 4. And then you could say this is really x times the derivative of 4 over 4 plus x. All right, what the heck is this? Well, you should be able to differentiate this thing. You can just use a nice little chain rule or something like that, right? Call this 4 times 4 plus x to the negative 1. And then you're going to get like a negative 4 over 4 plus x squared. And then you can multiply that thing by x. So we should end up with something like this. That's x times the derivative of 4 over 4 plus x. And that's what the Taylor series, or that's what this function is here. The interval of convergence, again, is negative 4 to 4. But because we noticed that this kind of looked like a derivative rule, we were able to connect this to a geometric series and then connect that to a function and differentiate that function, which is pretty cool. That's a hard thing to do. So what you should start noticing is that if there are x's multiplied, maybe try and make it look like a derivative of something. Now, you could try and think of what would happen if there were x's divided. Well, the times that we divide by x's are when we're integrating things, antiderivatives. So you can try and connect things to derivatives and antiderivatives and see if you can force a geometric series or something else that you recognize. Not easy to do. All right, last example. Let's evaluate this convergent series. You can test this series to see if it converges, maybe like a comparison test or a limit comparison test would do it, or what I would probably just jump right into is either a root or a ratio test for something like this. But we can try and show that it converges. This isn't a power series because there aren't any x's, so we just have convergence or not, right? It's not an interval of convergence anymore. But once we show that it converges, we used to just stop there and say, okay, cool, it converges. But what I want to know is, what does this converge to? What is this thing? And that's a hard question. So what I want to do is see if we can write this as a power series of some function, or for some function, and then see if we can connect this to a function output. What I'm going to do this is to just rewrite this series a bit. I'm going to say this is just me shuffling terms around. You can say this is really 4 times k times 1 over 5 to the k. And now you might be able to see I've got this same kind of structure that I had earlier, right? So what I'm going to do is I'm going to write this as k equals 1 to infinity of 4 times a fifth. So I'm going to steal one of the copies of a fifth. And now I've got a fifth raised to the k minus 1. Cool. Now what I'm going to do is I'm going to define this as a function. Well, first I'll write it as 4 fifths times this series. Oops. From k equals 1 up to infinity of k times a fifth to the k minus 1. And I'll take this thing and I'm going to define this as f of 1/5, where f of x is this power series. So this is just a function evaluated. Okay, so now what we can do is we can say, let's consider this f of x function that I'm saying this is equal to. Let's look at the power series version of this. This is k times x to the k minus 1. And just like before, I'm going to say this looks like a derivative. And then I can say, well, then that's the derivative of the whole sum of the x to the k's. And this, again, is just a nice, oh boy, that's an ugly brace. Let me fix that. This is just a nice old, oh man, there we go. Geometric series. Yeesh, sorry about that. All right, so this is really the derivative of 1 over 1 minus x for the absolute value of x being less than 1. All right. So then what we can do is differentiate this. So we have negative 1 over 1 minus x squared, but then the chain rule says we're going to multiply by a copy of negative 1, so it's really positive 1. And again, our interval of convergence doesn't change. It's the absolute value of x less than 1. So if that's our function, then what we can do is say 4 fifths times f of 1/5 is really 4 fifths times 1 over 1 minus a fifth and I got to square the bottom. So this is 4/5 times 1 minus a fifth is 4/5. 4/5 squared is 16 over 25, but then I'm looking at the reciprocal, so it's 25 over 16. And then we can see this is really 5 over 4. So this series here converges to 5/4. Okay, well, why is that helpful at all? I mean, that's cool. We've answered a question that we weren't able to answer before. We can connect this to some stuff and figure out what this actually converges to. But what's interesting is that this is really useful in something like statistics, because what this is an expected value. It's an expected value of the number of flips it's going to take to get heads in a situation where you have some probabilities and stuff like that. It relates to a binomial probability kind of and a long run situation. But essentially, this is an expected value, almost like a mean of a distribution, of a discrete distribution. And you set these things up using sums or integrals depending on the case. For discrete distributions, we'll use these series. And you can evaluate these series now using some of these kinds of tricks. So that's pretty neat. So that's everything that we've got. Oh, I did have another slide where I wrote that out nicely so we could see it. Oh well. But that's everything that we've got. Let me go back here. This is all we really need. There's a lot going on in here, and these examples at the end are probably pretty difficult. But hopefully what we'll start recognizing is that these Taylor series or power series are really, really useful when we can connect them to functions that we know about, because then we can evaluate functions instead of evaluating a series. Or we can work with the series when it's a little bit more convenient to deal with a whole bunch of terms added together as opposed to working with a kind of difficult function. So that's where these Taylor series really shine. There are tons of other uses for these that I'm sure you'll all encounter in your other studies, right? As you get into some of your other science classes and things like that, you'll see Taylor series pop up every now and then. So hopefully that's a nice thing to see when you see it. But for now, here's a bunch of ways that we can work with these Taylor series to make our lives a little bit easier. All right, that's all that we've got for Taylor series. So we are wrapping that up for now, although I'm sure you'll have some more interest in this and play with it more on your own time and look up some really cool extensions of Taylor series and things like that. But other than that, that's all we've got. Good luck.